Okay, so good morning, everyone. It's nice to see all of you here today. So I hope that you are all feeling well. So I would like to let everyone know that today's session is being recorded. Okay, so also Dr. Joss Darling, a senior lecturer from the Mechanical Engineering Department, is with us today. And he is going to observe our session and provide me with feedback afterwards. Okay, so last week we considered how external diffusion affects the overall rate of reaction in two-phase catalytic processes. So using what we know about surface reaction kinetics, internal diffusion and external diffusion, which are all taken account into the overall effectiveness factor, we derived the design equation for a packed bed reaction. Yeah, so along the length of the two-phase reactor. And of course, you also now know how to determine the concentration profile inside the catalyst pellets. Okay, so we are now extending this to three-phase catalytic reactors. Okay, so we have done a lot of maths in topics 3 and 4 to derive the concentration profile. Okay, to derive the concentration profile in catalyst pellets and the effectiveness factors as well. So in this topic, we will build on what we already learned. So there will not be a lot of maths in this topic. Okay. So last week, I also provided you with a pre-recorded video, which takes you through the first part of this analysis. So let's have a brief recap of what was in the video lecture. Okay. So we started off by reviewing the steps in a three-phase reactor, which we also covered in one of the active learning activities in one of our LOIL sessions a few weeks ago. So the steps in a three-phase reactors are very similar to two-phase reactors, but now we consider the absorption step for the gaseous reactants. So now we have absorption, external diffusion, internal diffusion, and surface reaction. Okay, but before we proceed, there is a bit of a background noise. So could you please check your microphone? So please make sure that you are muted. Okay, thank you. Okay, and then after discussing the steps in a three-phase catalytic reactors, we went on to define the rates of each of these steps. And we showed that at steady state, these rates should be equal and that the overall rate of reaction, so here, I hope you can see my slide. So this overall rate of reaction is equal to the concentration of reactant A at the gas-liquid interface divided by the sum of resistances. Okay, so we have the resistance due to gas absorption. So this is 1 over kBAB. And then we have the resistance due to external diffusion, so 1 over Kc. APM. So this is the coefficient for external mass transfer. This AP is the external area of the catalyst pellet, and M is the catalyst loading. And then we also have the resistance to internal diffusion and surface reaction. So here we have 1 over M. So M is the catalyst loading. Eta, so that's the effectiveness factor. It takes into account the effects due to internal diffusion and surface reaction. And K is our reaction rate constant. Okay? So that we can analyze experimental data to understand more about the three-phase catalytic process taking place, we rearrange this expression like this. Yeah. So the concentration of reactant A at the gas-liquid interface divided by the reaction rate, okay, capital RA, this is equal to the sum of the three resistances. Okay, so this is very useful because if we obtain data in the lab, So we obtain this CAI divided by RA at different catalyst loading M. Then we can plot our data, and then we can fit a trend line and get a measure of the various resistances. Okay, so how do we get these data? So for CAI, we can measure the partial pressure of A, Henry's law. We measure the change in concentration over time to get the rate of reaction. And then we do this different experiments with different catalyst loadings M. Okay, so catalyst loading M, if you can remember, this is the mass of catalyst per unit volume of reactor. Okay, and then we can plot CAI divided by RA versus 1 over M, and we fit a trend line. Okay, so the y-intercept of this plot is the resistance due to gas absorption, and the slope is the combined specific resistance due to external diffusion. So RC is the resistance due to external diffusion, and RR is the resistance due to internal diffusion and surface reaction. Okay, so the higher the y-intercept, the larger the resistance to gas absorption. And the steeper the line is, the higher the resistance to external diffusion, internal diffusion, and surface reaction. Okay, so what do you think we want? Okay, if we want to minimize the overall resistance in our reactor, how do we want our plot to look like? Anyone? So in terms of the y-intercept and the slope, what do we want? To obtain the highest rate as possible. Okay, I can hear. Just please go ahead.
Do you want to have a small slope and you want it to be with a low y-intercept as well? So kind of like flat and low?
Okay, excellent. So that's Alfie. Thank you, Alfie. So that's what we want. Okay, exactly what we want. Low. We want low and low here. So small y-intercept and flat. Okay, we want low and flat so that the resistances due to the are small and the we don't to economics. Okay, so our reactor will not be that expensive if we have high rates. Okay, so you can do these experiments for various catalyst particle sizes. Yeah, so here we have different catalyst particle sizes, and we saw that the combined resistance, so RCR, so this is combined resistance due to external diffusion, internal diffusion, and surface reaction. It decreases with decreasing catalyst particle size. Okay, and then you can also perform experiments with different gas bubble sizes. Okay, using different spargers. Okay, so one way of controlling the bubble size is using a particular type of sparger. You can also control your agitation rate. And we've seen from the video lecture that the resistance due to gas absorption, it decreases with decreasing gas bubble size. Okay? So it is very easy to separate the resistance due to gas absorption, RB, and the combined resistance due to external diffusion, internal diffusion, and surface reaction, RCR. Okay, so again, the y-intercept of the plots, okay, CAI divided by RA versus 1 over M, that is the resistance due to gas absorption. And the slope is RCR, okay, so combined resistance due to external diffusion, internal diffusion, and surface reaction. Okay, do you have any questions about the video lecture? Okay, excellent. So I wanted you to think about how we can separate out RCR. Yeah, so I gave you a homework. We wanted to separate out RCR into its various components: external diffusion, internal diffusion, and surface reaction. So this is important because knowing which of these resistances is highest, we can do something to lower that resistance, which will have a significant effect on the overall rate. Okay, so this is more effective than changing parameters at random. Yeah, so for example, you've seen before in topic 3 that increasing the temperature of a process that is controlled by internal diffusion doesn't have a significant effect on the rates.
But decreasing the particle size does. The step that has the highest resistance controls the rate. So this is the step that we need to target.
So did anyone come up with any ideas on how to separate out RCR into its various components? So no worries. I just really want you to think about it before we discuss it. I needed to capture my handwriting. I made a pre-recorded video explaining how to separate out RCR into its various components. Yes, if I do it live, then you won't be able to see my handwriting. So it's better this way than me talking about the content of the slide. So let's watch the video together. And if you have any questions, just raise your hand. So I'll share the video now. And let me know if there are any issues. Okay, I can see a raised hand. Yes, Akina, please go ahead.
Yeah, hello, Shiri. Can you hear me?
Yes, I can hear you.
Yeah, just without doing any graphs, could you actually use like the stuff like the Biot number and the Taylor modulus to like work out if it's internal, like without plotting, or could you not do that?
Yes, you can use those measures, but they are only applicable for two-phase reactors. For
Oh,
three-phase reactors, they don't include the gas absorption step. But if you're only looking into the three effects, fusion, internal diffusion, surface reaction, you can use the relationship.
thanks.
Okay, anyone else? So let me know if you cannot hear the audio in my video, yeah? And if you have any problem. Okay, so let's do it.
Using our slurry reactor, we can perform experiments at various catalyst loading M, okay, and at different catalyst particle sizes. We denote catalyst particle size as dP, okay, so particle diameter. And we can measure the partial pressure of A, from which we can calculate the concentration of A at the gas-liquid interface, which we denote as CAI. Okay, so we can calculate this from the partial pressure using Henry's law. And we can also measure the rate of the overall reaction, capital RA. So we just measure the change in concentration of the reactant over some period of time. So say in your experiment, okay, so you performed it at different catalyst loading. So say at M1, M2, M3, and so on. And then for every catalyst loading, you also perform a set of experiments at different catalyst particle sizes. So you have DP1, DP2, DP3, and so on. So you can tabulate your data like this. Okay, so here, so just get the inverse of your catalyst loading. So 1 over M1, 1 over M2, 1 over M3, and so on. And then here, for the columns, we have the DP1, particle size 1, DP2, DP3, and so on. And for every combination of catalyst loading and particle size, you will have CAI divided by RA. Okay, so you'll have that for each combination of catalyst loading and particle size. Okay, so therefore, you'll be able to plot CAI over RA versus 1 over M. Okay, so plot this for every particle size dp. Okay, so your plot may look like this. Okay, so say this is for catalyst particle with size dp1, dp2, and dp3. Okay, and for each plot, you will be able to calculate the slope. Yeah, so say for this one, the slope is equal to RCR1. For this one is RCR2. This one for RCR3. Okay, so you'll have another table. Okay, so here you can have particle diameter and the slope. The slope is the RCR, okay, combined resistance due to external diffusion, internal diffusion, and surface reaction. And your data may look like this. So for particle diameter 1, your slope is RCR1. For diameter 2, you have RCR2. And then for diameter 3, you have RCR3. Okay, and the next thing that you should do is to plot the log of RCR versus the log of the particle diameter. Okay, so your plot may look like this. So plot these data points. So this is log of RCR on the y-axis and log of the particle diameter on the x-axis. And you may have like this. Okay, so plot your data points. Okay, and then you fit a trend line. So the slope of this, okay, so the slope of this line will tell you what the controlling step is, okay, whether it is external diffusion, internal diffusion, or surface reaction. So again, we separated out already the resistance due to gas absorption. So RB is just the y-intercept. Of this plot here. So CAI RA versus 1 over M. So let's show why that is. By plotting this log of RCR versus log of particle diameter, you can separate out the resistance due to external diffusion, internal diffusion, and surface reaction. So we have this relationship, CAI divided by the rate, RA. This is equal to 1 over KBAB plus 1 over M, 1 over KC, AP, plus 1 over eta, K. Okay, so this is the resistance due to gas absorption, RB. And this is the resistance, this is the combined resistance due to external diffusion, internal diffusion, and surface reaction, RCR. Okay, so we are interested in this, RCR, and we wanted to separate it out into its components. So external diffusion, internal diffusion and surface reaction. So RCR from this is 1 over Kc AP plus 1 over eta K. Okay, so remember that Kc, that's your external mass transfer coefficient. AP is the external surface area of your pellet. Eta is the effectiveness factor, which takes into account the resistance due to internal diffusion and surface reaction. And K is your rate constant, reaction rate constant. Okay, so let's consider case A, where we have small particles. Okay, so when we have small particles, the external surface area of your pellet, AP, is large. So therefore, this term here is small. Okay, so 1 over Kc AP is significantly smaller than this term, 1 over eta K. Okay, also, at small particle diameter, so when your particles are small, the Tila modulus phi is small. Okay, so this is from topic 3. Okay, and if you remember, if the Tila modulus is small, the effectiveness factor, eta, tends to 1. Yeah, so therefore, 1 over eta K is approximately equal to 1 over K, because eta tends to 1 for small Tila modulus, which is true for small particles. So therefore, RCR is approximately 1 over K. Yeah, because we can drop this term here, and eta tends to 1. Okay, so therefore, this is not, so RCR is not a function of the particle diameter. Okay, because K, the rate constant, the reaction rate constant, is not a function of the particle diameter. Okay, so therefore, if we plot the log of RCR versus the log of the particle diameter, the slope is 0. Yeah, because the combined resistance, RCR, is not a function of the particle diameter. Okay, or another way of seeing this is that RCR, so let's convert this to an equal sign, and we need an arbitrary constant, say alpha 0 over K. And then we take the log of each side of the equation, so we'll have log of RCR is equal to the log of alpha 0K plus 0 times log of dP. Okay, so this is our slope. When we plot this, log of RCR versus log of dP, our slope is this, 0. Okay, so that means that if the slope of this plot is 0, then the limiting step is the surface reaction. Okay, because we said before in topic 3 that for small particles, so for small values of Tila modulus, the surface reaction is controlling over internal diffusion. Okay, so if the slope is 0, the process is controlled by surface reaction. So this is surface reaction limited. So let's consider case B, where your particles are moderately sized. we know from topic 3 that for small to moderately sized particles, we have two choices for the step that is controlling the process. So it is between surface reaction and internal diffusion. Okay, so moderately sized, we know that internal diffusion is limiting. Okay, so looking at this expression, so RCR, so for moderately sized particles, this term still dominates. Okay, because if it's moderately sized, this AP is still significantly large. So this term here is still significantly smaller compared to this term. So our combined resistance, RCR, is still approximately equal to 1 over eta k. But now, for moderately sized particles, the Tila modulus is much bigger, much larger than the Tila modulus here when your particles are small. Okay, so your Tila modulus now is large. And we know from topic 3 that for large Tila modulus, your effectiveness factor eta tends to 1 over the Tila modulus. So that means that RCR is about, okay, so we just substitute in this one here. So eta tends to 1 over Tila times K. Okay, and say we have a first order reaction. Okay, so that we can easily write out the expression for the Tila modulus. So this is approximately equal to, okay, the Tila modulus divided by K. From topic 3, we know how to write the Tila modulus for a first order reaction. Okay, so the Tila modulus for first order reaction is, okay, so dP, the particle diameter, divided by 2 times the square root of K times specific surface area, SA times the catalyst particle density divided by the effective diffusivity. Okay, and then we also have a K here from here. So the combined resistance, RCR, so these are all constants, and these are constants too. So we can say that this is, okay, proportional to the particle diameter. Okay, and if we convert this into an equal sign, so you'll have RCR is equal to some constant alpha 1 times dP. And then if we take the logarithm of both sides of the equation, then we'll have ln RCR. So log of RCR is equal to log of alpha 1 dP. Okay, this is equal to ln alpha 1 plus ln dP. Okay, so log of RCR is equal to log of alpha 1, so this is constant, plus 1 times the log of dP. Okay, so if we plot the log of RCR versus log of dP, okay, so the plot of this, okay, has a slope of 1. Okay, so that means that if the slope of this plot is 1, then internal diffusion is limiting. Now let's consider case C, where we have moderate to large particles. Okay, and we know from topics 3 and 4 that for large particles, external diffusion could be limiting. Okay, so external diffusion could be the rate limiting step. So now our combined resistance, RCR, is approximately equal to 1 over KCAP. So we can drop this term because for large particles, the external surface area, AP, is small. So this term here is significantly larger than this. So we can write RCR approximately equal to 1 over KC AP. So we can easily work out AP. So AP is the external area of the pellet divided by the mass of the pellet. The external area of our catalyst pellet. Okay, so we assumed it to be spherical in shape. So the external area is just equal to pi times the square of the diameter. And the mass of the pellet can be written as the density of the particle times the volume. And the volume of a spherical pellet is equal to pi times the cube of the diameter divided by 6. Okay, so simplifying this, is pi will cancel out. dp squared will cancel out with dp squared here, so you'll be left with 1 dp here. So the external area per unit mass of catalyst, AP, is equal to 6 divided by dp, okay, the particle diameter, times the density of the catalyst particle. So there are two cases that we need to analyze. The first is when there is no shear stress between the particles and the fluid. And the second is when there is a shear stress between the particles and the fluid. So the shear stress is the force acting parallel to a unit area. So meaning in the plane of the surface it is acting on. And the shear stress will be a function of both the agitation or steering rate and of the particle size. Considering the first case, so no shear, if the particles are small enough, then they will move with the fluid motion and there will be no shear between the fluid and the particles. Okay, so in this situation, the Reynolds number is small. Okay, so if we look at Frost-Link correlation, okay, so we had this in topic 4. So this is equal to the Sherwood number equal to 2 plus 0.6 times the Reynolds number raised to 1/2 times the Schmidt number raised to 1/3. So for no shear case, the Reynolds number is small. Okay, so you should have learned this from your mass transport phenomena. Okay, so no shear, Reynolds number is small. The Schmidt number is almost constant. Because as you can remember, the Schmidt number is just a function of the properties of your fluid. Yes, if you can remember, Schmidt number is equal to the viscosity divided by the density and the diffusivity of A in B. Okay, so this is not affected by the particle size or the agitation rates. So Reynolds number is small and is significantly smaller than 2. So therefore, the Sherwood number is approximately equal to 2. And we know that the Sherwood number is equal to the mass transfer coefficient Kc times the particle diameter dp divided by the diffusivity of A and B. Okay? And this is equal to 2. So therefore, Kc from here can calculate this as 2 times the diffusivity of A and B divided by the particle diameter, dp. Okay. And now, substituting Kc and AP into our RCR. So RCR from here, okay, this is equal to 1 over Kc AP. Okay, so Kc is this. So we have 2 dAB over the particle diameter, and AP is this. Okay, so we have 6 dP over rho c. And then simplifying this, okay, so we'll have rho c dP squared divided by, okay, so we have 2 times 6, so we have 12 dAB. Okay, but the density and diffusivity are constants. So we can say that RCR is proportional to the square of the particle diameter. So if we convert this into an equal sign, so we'll have RCR is equal to some constant, which we call alpha 2 times the square of the particle diameter. And then taking the logarithm of both sides, so we'll have log of RCR is equal to log of alpha 2 times the square of the particle diameter. And okay, using the property of logarithm, so we can write the log of RCR is equal to the log of alpha 2 plus the log of the square of the particle diameter. Okay, but this is also equal to the log. Okay, we can also write this as log of RCR, log of alpha 2 plus 2 times the log of the particle diameter. Okay, so therefore, we can plot Ln, okay, or the log of the combined resistance versus the log of the particle diameter dp, and the slope of this. Okay, so from here, so this is the slope of this plot. So slope is equal to 2. So if the slope is equal to 2, then external diffusion is the rate limiting step and there is no shear. Lastly, let's consider the case when there is shear between the particles and the fluid. So we have case 2, shear between particles and fluid. So if there is shear between the fluid and the particles, then we know from your mass transport phenomena that the Reynolds number must be large. So looking at the Frost-Link correlation, so we have the Sherwood number. This is equal to 2 plus 0.6 times the Reynolds number raised to 1/2 times the Schmid number raised to 1/3. So therefore, we can ignore the 2 because the Reynolds number is large. So this term dominates. Okay, so this is significantly larger than 2. And the Schmid number is more or less constant because the Schmid number is just a function of the fluid properties, the viscosity, density of the fluid, and the diffusivity. Okay, so we can write Sherwood number proportional to the square root of the Reynolds number. And we know that the Sherwood number is equal to Kc times the particle diameter times the diffusivity of A and B. So this is proportional to the Reynolds number, which is the density of the fluid times the particle diameter times the velocity u, velocity of the fluid u, times the viscosity of the fluid raised to 1/2. Okay, Reynolds number raised to 1/2. So therefore, Kc, so from this, we can write Kc is proportional to the square root of the fluid velocity u divided by the particle diameter dp. Okay, because dAb, the density and the viscosity are constants, and you have square root of dp on this side and dp here on this side. So you'll have this Kc proportional to the square root of the velocity of the fluid divided by the particle diameter. So now, okay, our RCR is approximately equal to 1 over Kc AP. Okay, so this is for moderate to large particles. Okay, or rather, this is approximately equal to 1 over Kc times the external area, external surface area of the pellet. And we know that the external surface area is equal to 6 divided by the particle diameter times the density of the particle. Okay, so we can substitute Kc into here and AP into here. So we'll have RCR approximately equal to 1. So Kc is this, so we have 1 over U dP raised to 1/2. And we have AP, which is equal to 6 dP times rho c. Okay, so we can say that, okay, so we have dP raised to 1/2 here, and then we have dP here. So we can say that RCR is proportional to, so this is in the denominator here, and this one, this whole term here is in the denominator. So we can say RCR is approximately equal to dP raised to 3 over 2. Okay, so because you have 1/2 here and 1 here. Okay, if we convert this proportionality sign to an equal sign, then we'll have RCR is equal to, okay, so say some constant alpha 3, okay, times dP raised to 3 over 2. Okay, and then taking the logarithm of both sides, we'll have log of RCR is equal to the log of alpha 3 times the particle diameter times 1.5. Okay, 3 over 2. I can write this as ln RCR is equal to the log of alpha 3 plus 1.5 times log of dP. Okay, so therefore, plotting RCR versus the log of the combined resistance RCR versus the log of the particle diameter dP will give us a slope of 1.5. Okay, so the first link correlation is not the only correlation that is available for calculating the mass transfer coefficient Kc. So as we mentioned at our IPT, we have other correlations. So for example, the Satterfield correlation. Okay, so Satterfield correlation. So you have the square of the Sherwood number. This is equal to 4 plus 1.21 times Reynolds number times the Schmidt number raised to 2/3. Okay, so if you use this correlation instead of the Frusling correlation here, then you'll end up with RCR proportion or equal to alpha 3 times dp raised to 1.7. Okay, instead of 1.5, you'll have 1.7 for if you use Satterfield correlation. Okay, so therefore, the slope of the log, the slope of the plot of the log of combined resistance versus the log of the diameter is 1.7. Okay, so if the slope is between 1.5 to 1.7, then you can say that this is external diffusion limited, and there is shear between particles and fluid.
The next few slides just summarize what I did on paper. Okay, so we plot the log of RCR as a function of the particle diameter. And if the slope is 0, it's surface reaction limited. If the slope is 1, then internal diffusion is the controlling step. And slope of 2 means that it is controlled by external diffusion and there is no shear stress. And a slope between 1.5 and 1.7 means that the process is controlled by external diffusion and there is shear between the particles and the fluid. Okay, so any question? So some of you may be wondering why in case B. So here we have moderate size particles, and in case C, we have moderate particles again. Okay, but note in case C, it is not just moderate particles. Okay, it is moderate to large particles. So there's a difference. And also, because particle size alone does not determine what the limiting step is. Okay, so there are other factors such as the pellet material and the fluid properties that determine the rate limiting step. So the transition between different limiting regimes will occur at different pellet sizes for different systems. Okay, so if you use just the particle size to determine what the rate limiting is, it's quite subjective. Okay, it's not very defined. So it is very important not to use particle size alone to determine the rate limiting step, and instead use the experimental procedure we have discussed today. Okay, so you should create your plots. So that will give you a better way of determining what the rate limiting step is. We will recap from the beginning what we have talked about slurry reactors. Okay, so we want to identify which step is rate limiting for the slurry reactor. So we found that CAI over RA could be written as the sum of the three resistances. And then we can plot this and get an insight on the strength of the gas absorption resistance and the combined resistance. And then we can do the experiments at various catalyst particle sizes and then plot this. So this is the slope of your first plot. Okay, so you'll have different values of this for different catalyst particle sizes. And then plot that with the log, so against the log of your particle size diameter. So if the slope is 0, it's reaction limited. Slope of 1, it's internal diffusion limited. And
If the slope is between 1.5 and 2, then it is external diffusion that is controlling the process. Here is the general procedure for analyzing a slurry reactor.
First, we do a series of experiments with different catalyst loadings M and plot CAI divided by RA as a function of 1 over M. And then we get the slope and the y-intercepts. So the y-intercept will tell us the resistance due to gas absorption, and the slope will give us the resistance, combined resistance due to external diffusion, internal diffusion, and surface reaction. And then we do this at different catalyst particle sizes, and then we create another plot. So log of RCR versus log of DP, and then determine the slope. So look at the slope of this plot. Okay, if it's 0, it's surface reaction limited. If it's 1, it's internal diffusion limited. So between 1.5 or 1.7, external diffusion limited with shear, and if it's 2, then it's external diffusion without shear. Okay, so any question? You may find the slope to be at an intermediate value, so say 0.5, okay? So between 0 and 1, okay? What do you think that means? Okay, so that means that more than one factor is controlling, okay? So if it's 0.5, it is a combination of the surface reaction and internal diffusion. Okay, so using this information, you can now target specific aspects of the reactor to improve its performance. So this is a very useful approach, because if you can improve the performance of a reactor, then it can save your company a lot of money, and you may get promoted as well. Okay, so now that you know how to find out what the limiting step of a catalytic process is, you need to know what variables can improve the rate of that step, and therefore the overall observed rate. Okay, so if you find that gas absorption is the rate
controlling step, then there are several things you can do to improve it. Increasing the agitation will help
to break up the bubbles and make smaller ones, so a larger surface area is created. And the higher the shear rate, okay, so the higher the mass transfer coefficient. Okay, so you can change the steering rates. So the reactor design can also be changed to improve gas absorption. So for example, changing the impeller type can improve the mixing in the tank. You can tweak the gas distributor to change the size of the bubbles, and other design features that can improve mixing and prevent dead zones. So finally, you can also increase the concentration in the gas phase, so that can improve the performance too. So this can be done by increasing the pressure or going to a more pure gas feed. So basically, you are increasing the driving force if you do that. Okay, so overall, in order to improve the gas mass transfer for a process that is controlled by you can control the steering rates, reactor design, and concentration of the gas phase. Okay, what about temperature? Okay, so temperature has a limited influence on the process if the limiting rate is gas absorption. Okay, why is that? Okay, so remember the temperature, it affects the equilibrium between the gas and the liquid. So what parameter does it affect? So when you think of gas absorption into the liquid phase, what is affected by the temperature?
The partial pressure of the gas.
Yes. And then if the partial pressure has changed, okay, it's very close to that. Yeah. So changing the temperature, so you are absorbing the gas phase into the liquid phase. Yeah. Do you remember your solubility? So you have solubility, yeah, solubility of gas reactant in the liquid. Yeah. So that can affect the temperature can affect that. So what happens to solubility when you increase the temperature? Solubility of the gas phase into the liquid phase.
It decreases.
It decreases. Okay, thank you. And what do we want? Do we want it to be more soluble? Do we want our gas phase to be more soluble in the liquid phase, or less soluble? Okay, remember our reactant, they need to reach the catalyst active sites. Yeah, so we want more gas dissolved in our liquid. If we want to increase the solubility, we would decrease the temperature. Okay, but if you decrease the temperature, there are other parameters that will get affected. Yeah, like the reaction rate constant. So we know that the rate constants, the reaction rate constant, that can decrease with decreasing temperature. So you have this opposite effect. Okay, so in general, temperature has a minor influence, and you have to be careful as well changing this if gas absorption is dominating. So this will not always result in increased reaction rates. Okay, and then finally here, so in this column, you have parameters that have insignificant influence. Okay, so these are variables associated with the catalyst particles and liquid phase reactants, such as the catalyst loading and particle size. They have little or no effect on the overall rates, since the process is controlled by what is taking place in the gas-liquid interface. So for example, here, you don't have to increase the concentration of active components on catalyst. So it means, when you increase the active components, so increasing like the precious metals. So if you're using precious metals as your active sites, then that's very expensive, but it will not have significant effect on the rates because the process is controlled by gas absorption. Okay, so any question? Okay, so I'm aware of the time. So we will carry on discussing this next week. On Moodle, I have uploaded a problem sheets for this topic. So please have a go at that, and we will also discuss the solution at our next meeting. Okay, and then all of the materials from today, I will upload them to Moodle after the session. Okay, so last opportunity for questions. We have 1 minute. Okay, so if you think of anything, if you have any question, if something comes up later on, please use our Padlet board. Yeah, so post your question and I'll reply there. Okay, so thank you for joining, everyone. It's nice to see you all. So have a nice day and I'll see you next week.
Thank
Okay,
you.
bye.
Thank
Thank
you.
you.
Thank you.
Thanks.
Thank you. Thank you.
Thank you.
Thank you. Cheers.